Imagine that you're the marketing head of a company selling cars, and hopefully they're not Volkswagen, all over the world in 200 different locations. Now, the company allocates a huge marketing budget to you, which you hopefully spend on advertising. Now, the question that you face is, how much should you be spending on the three available options, which are television, radio, and newspaper? While you could go with your gut feeling and the previous year's advertising allocation data, but a more appropriate approach would be perhaps to go to your sales team. Ultimately, through an effective marketing campaign, what you're trying to maximize is your sales. So in order to maximize your company's sales, what should be the most ideal marketing plan? Well, our first goal is to establish any evidence of a relationship between advertising expenditure and sales. And ridiculous as this may sound, if the evidence is weak, then one might argue that no money should be spent on advertising. If we do succeed in establishing a relationship between the advertising budget and sales, the next thing that would be of interest to me is what is the strength of this relationship? In other words, given a certain advertising budget, can we predict sales with a high level of accuracy? Or is a prediction of sales based on advertising expenditure only slightly better than a random guess? Next, do all three media, that is television, radio, and newspapers, do all of them contribute to sales? Or do just one or two of the media contribute? To answer this question, we must find a way to separate out the individual effects of each medium when we have spent money on all three media. If we have established that each of the three media are contributing towards sales, then how accurately can we estimate the effect of each medium on sales? For every dollar spent on advertising in a particular medium, by what amount will sales actually increase? How accurately can we predict this amount of increase? How about predicting the future? For any given level of television, radio, or newspaper advertising, what is our prediction for sales? And importantly, what is the accuracy of this prediction? Is the relationship between advertising expenditure in the various media and sales a linear relationship? If it is, well, it's great news, as we can then get into something known as linear regression. If not, then as Douglas Adams states, don't panic. We will help you through that too. Well, we've asked a lot of questions here, and fortunately for us, all of them can be easily answered. We now move into the magical world of R. Before we get down and dirty with R, I would like to draw your attention to this book from where the advertising data has been taken. Trevor Hasty and Robert Tripshirani, who are co-authors along with Gareth and Daniela, have made this book freely available as a PDF download. It is highly recommended. You can click on this link here and download the advertising.csv data. Well, if you've never used R, this is what the data looks like in Excel. It's got 5 columns. The first one is just the ID corresponding to the 200 different locations where your company sells cars. The columns TV, radio, and newspaper are the expenditure in thousands of dollars on advertising. And the last column shows you the number of cars sold, again in thousands. Okay, now let's get into R. I use RStudio as my development environment. Now this is where I will be writing my commands. And this area is the console where the results of executing the commands will appear. First things first, let us set the working directory to the location of the data file. We can do this by using the set working directory function and specify the location of the file. You could also do this by going to Session, Set Working Directory, and choose Directory. Incidentally, I am executing the commands in this script by pressing Ctrl and the Enter key. Now that the working directory is set, let us import in the data. We will define a new variable called add_data, in which we shall read in the data file by using the read.csv function. Let us now look at what the data looks like. We can use the head function to have a quick look at the data composition. As you can see, this produces the first 6 observations in the data frame. We can also look at the structure of this newly created variable by using the str function. This shows that ad_data is a data frame comprising of 200 observations of 5 variables. These variables are the same as what we saw in Excel earlier. Now, one of the first questions that we asked in the introduction was, is there a relationship between sales and advertising spending? Well, for starters, let us look at only the spending on TV advertising and the sales. To do this, we first attach the data set. By doing this, we make our life a little more comfortable, as we will not have to type the name of the data set along with the variable that we will be working on every time we want to use this variable. We can then create a scatter plot by using the plot function. This command produces a scatter plot with expenditure on TV advertising on the x-axis and the number of cars sold on the y-axis. Now, looking at this plot, what do we conclude? Well, it definitely looks like that the more we spend on TV advertising, the more our sales go up. Secondly, the relationship does appear to be linear. By that, I mean that we could have a straight line which could adequately represent this distribution. But the question is, how do we draw this straight line? We could have a line like this, or perhaps this. Now, out of these 3, the green one definitely appears to be closest to reality. And why is that? Well, common sense dictates that this particular line is the one which minimizes the distance between these individual points and the line itself. So how do I get the equation for such a line? Recall from your geometry class in school, the equation of a straight line is given as y is equal to mx plus c. This equation requires 2 parameters. One is the intercept c, or where this line intersects the y-axis, and second is the slope m. As seen in this figure, the red line definitely has a greater slope or incline than the green one. So given the condition that our ideal line must minimize the distance between the individual points and the line itself, is there some way in which we can define the slope and the intercept? As a matter of fact, there is. Let us now define 2 new variables. Let capital X be the difference between the spending on TV advertising and the mean value of spending on TV advertising. Similarly, let us define another variable Y to be the difference between sales of cars in all 200 different locations and the mean value of cars sold. Now for our line, to get the magical value of slope, we take the sum of the product of x and y and then divide this by sum of x squared. Don't worry about why this is the right value. By using some calculus, it can be shown that this value indeed is the correct estimate. Now that we have the slope, we can estimate the intercept too, as the difference between the mean value of cars sold and the product of the slope and mean value of TV advertising. This is a direct outcome from the equation of the slope of a line. We can now plot this line on the scatter plot by using the AB line function, where A is the intercept and B is the slope of the line that we want to draw. And let us draw this line in blue. We could also draw all the line segments from these individual points to the regression line that we have just drawn. To do this, first let us define all the values of y for this line corresponding to x. We will create a new variable called y_new, and this will be nothing but the sum of slope into TV spending plus the intercept that we have just calculated. Next, we use the segments function, which takes in 4 arguments, the first two being the x and y coordinates of the starting point, and the next two being the x and y coordinates of the ending point of the line segments. So, to sum up, this blue line here is the one that minimizes the distance between these individual points and the line itself. Any other line will not. Fortunately for us, we don't have to go through all the calculations manually like we just did. We can use the linear modeling function in R called LM to regress sales onto TV advertising. Let us create a new variable called fit, in which we shall store the output of the linear model that we run for regressing sales onto TV advertising. We can have a quick look at the summary of a model by using the summary function. Well, there's a lot going on here. Importantly, I just want you to have a look at the intercept term and the slope, which is reflected against TV. These values are the same as what we had calculated manually. To confirm, let's see the value of intercept. As you can see, it is the same as what the summary of the model has generated. Similarly, the slope value is the same as what we are getting here in our linear model. In the next video, we shall have a look at the other values that the summary function has produced and thereby answer all the questions that we had asked in the introduction to this video lesson.